So what if we have some additional information? If we know that this amount of salaries did not just come from 3 different cities, but we actually sampled different types of businesses in the city to look at the wages across retail settings and wholesale settings. Now we have some additional information that we didn't have before when we were just looking at the variability among, of course, all the values, but then within the cities. Now we have a new way of looking at the variability also within retail or within wholesale. So this is new information. Effectively, we've just added now the ability to calculate some more means. And by knowing this information, would it help us make or see differences in salaries and wages earned across and among the cities? And the answer is going to be yes. Now we could expect that there's variation between each group. Here we have 3 groups. We still have 3 groups in the factor of city. But now we actually have 2 groups in a factor that I'm going to call business type. So business type has retail and wholesale. We have 2 different types. And when we sampled these 3 people from London, we now know that 3 of them were from retail. These 3 people were from wholesale. Wouldn't we have the same hypothesis that the wages earned of workers in London and wholesale are probably more likely similar within themselves, the same way that I would suspect that these 3 workers' salaries are likely more similar within themselves in London. Again, all this information helps us interpret the pattern that's going on. The shape of this might actually look familiar to you. If you remember, we were looking at contingency tables that had different cells. You can almost superimpose a contingency table here where there's a cell here of averages that you'd be able to add up of wholesale workers in London and retail workers in London. And then you'll notice we have marginal means here for those values. It's very similar to the shape and idea that we looked at for probability tables in prior sessions. So to highlight this a little further, we definitely have one factor here, which is going to be the city. It has 3 groups in it, or 3 levels, London, Munich, and Paris. And then we have another factor of business type, and it has 2 levels, retail and wholesale. Each of those would produce their own mean within their group. All of these would be retail scores that would add up to this. All of these would be wholesale scores that would add up to this mean. So we also have this additional really interesting question. Could there in fact be an interaction between these two factors? In other words, does knowing something about the city that the worker is in help, and knowing something that the industry business type that the worker is in help me make a decision about their wages? And that is really the power of Anova. So what we're really talking about here are these 2 ideas. There could be a main effect, which would be the differences among the groups on one factor, any one factor. So we had really 2 factors. We have a factor of city that we could be looking at differences across. We also have a factor of business type. We would consider those both main effects. So we have 2 possible main effects, which would be differences just across that factor. But we could also be looking at an interaction. The difference on one factor changes across levels of a second factor, or more factors, but we'll just be demonstrating 2. In that case, we would write the null hypothesis like this. There's no significant difference across wages between cities or across business types, and there's no significant interaction among them. Here's our 2 main effects: a possible main effect difference across cities, possible main effect differences between business types, but we could also predict that there's a significant difference in the interaction. And here's how we would frame that. First alternative hypothesis, that there is a difference in wages across cities. A second alternative hypothesis is that there is a significant difference in wages across business types. Those are our 2 main effects. Here is the interaction. There is significant interaction for wages between cities and business types, such that the wages earned in each city differs or depends on the business that they're in. That makes a lot of sense. I would suspect somehow that retail workers are paid something differently than wholesale workers. So it's not only that they're in a different city, but it might also depend on the type of business that they're in. Let's explore that in a two-way ANOVA. And this is what the output is going to actually look like. The first row is going to help us test to see if there is a difference in the first factor, which is city. In this case, we can see the p-value is now less than 0.05. We'll come back to this idea in just a moment. This is an amazing result because we had just looked at before and we saw there was no difference in wages across the city. Now we see that there is a significant difference in wages across the city. Why is that? Well, it's because we added new information. We added information about business type. And knowing something about business has helped us explain variance in the sample that I couldn't see before. Is business by itself a significant factor to explain differences in wages? Well, we're at p.06. My alpha level was at 0.05 in my hypotheses, so we have to reject the null hypothesis, or we have to accept the null hypothesis here. We cannot accept the alternative hypothesis. There's no significant difference for business. And then the last question I asked was, is there an interaction? Is the city and business have different levels of salary across them? And again, here we see a non-significant p-value. It's greater than 0.05. So I still have to retain my null hypothesis. The overall model statistic is here, and I would write the overall statistic this way, and this is actually what I'd be looking at first. These values, the first value comes, the 5 is coming from here in the table, 1, 2, 3, 4, 5, and this is the what's driving the 5 here, and the 12 you can see here is the mean squared effectively within degrees of freedom, and so that's where we get the 12. And now we have our F statistic overall, and look, it is significant. When I see an overall F statistic here, it's just telling me that there's some difference in the factors or across the groups, and we know that where it is. It's right here. City was the one significant factor. It will be the case when we have an overall F statistic that's significant. We'll have to look and to the analysis and see which factor, effectively variable or independent variable, you could think of these as independent variables, was significant. In this case, it was driven mostly by city, but we have no significant interaction. So here's the full interpretation. We would reject the null hypothesis. There is a statistically significant difference, p less than 0.05, across wages. Wages are significantly different across the cities, and this is the way that we would write the fact here in cities. This is the F statistic for the city. Here's the 2, here's the 12, and the F statistic I got right here, because this is the row that's helping me test for that difference of city, which is the one that I'm interpreting here, and the p-value is 0.03. This F statistic is for the overall model, and I'll show you where we get that out of SPSS. There is no statistically significant difference in wages across the different business types, and there's no significant interaction. And I'm specifying that's because their p-values were greater than 0.05. If I had gone in a priori before I started the test with a p-value of 0.1 for our factors, then I would have changed this interpretation. In fact, then I could report that there is a significant difference between city and business, but if I keep my p-value at 0.05, I cannot do that. I have to reject it. So these are some different ways to interpret that. Here's the actual output from SPSS that we would get. If you compare this to the prior slide, you'll see the results are identical. This is our significance level. So we have a significant difference between the cities, not for the businesses, and no significant interaction of city and business. So this is the way that we would interpret this by looking at data overall. This is the number that we're going to be putting into our F statistic. This is how I'm drawing on the overall. Overall is actually this 5, 12. I think I have that circled here in just a moment, so that you can compute that, and then you can see where those other values are. Same information that we just got in the prior, it's just located in a slightly different place, and this is how we would plug it into an overall interpretation. So you can see we have a significant difference in wages across those cities. This is a significant, what we say, a main effect. Now, if we were looking for, or especially if we had suspected further that we had made a hypothesis of a specific difference, we would definitely be able to do this next step. It's probably a best practice to do that, but nevertheless, we want to find out where that difference is, because the F statistic for the Anova just says there is a difference. We don't know between which cities. For that, we're going to need some additional tests. We want to be able to test the differences between London and Munich, London and Paris, Munich and Paris. That's all of the different pairwise comparisons that we can make between those means. If this had been significantly different, we would actually already know that from the F statistic, because there's only 2 levels for business type. But when there's 3 levels, we don't know which differences could be driving that, and that's why we need these additional tests. So we run those tests. These are the actual means between the cities, which is what I'm going to need to have to run the test. And when we run the test, called pairwise comparisons, it allows us to look at each pair individually. So this is the way that SPSS outputs that. A lot of numbers here, but they're really pretty simple to interpret. These are just the mean differences. So if you come up above and subtract London's mean from Munich's mean, London's mean from Munich's mean, you'll get this difference, 0.133. And we can see whether or not that difference is significant right here. If this value is 0.05 or less, we would say it's significant. Here, it is greater than 0.05, so we cannot say that this is the difference. How about London to Paris? So that would be comparing the 12.15 to the 12.60. The difference there is a minus 0.45. And here we do see a significant result. So that mean difference, which is effectively wages, is significantly different. That is one of the comparisons that's causing this overall significant difference that we saw in the prior slide. Now we continue with those comparisons, and you'll see these repeat because they continue down by pairs. We can see that this is our next one that's going to be different, is Munich and Paris. This is also significantly different. It's p less than 0.05. So this difference between Munich and Paris, that's a significant difference as well. We've already looked at, I think, the Paris-London difference right here, and we already looked at the Munich-Paris difference right here. And so this is the same information just repeated in the final rows. So it's redundant to the interpretation that we had above. So in summary, we've got 2 differences. We have a significant difference between London and Paris, and a significant difference between Munich and Paris in terms of mean salaries. The pairwise comparisons would have us reject the null hypothesis. Average wages in Paris, which are $12.60, are significantly higher than the average wages in London, and significantly higher than the average wages in Munich. And that's how I would write that result up if I was going to be reporting it, for example, in a report. And notice that I've had the p-value, so it helps me understand at what level it is significantly higher in both cases, at p.05 or less. This is what the actual chart that SPSS produces of those differences. So now we can actually see that. We know that the difference is between Munich and Paris and between London and Paris. And the test showed us there's no difference between London and Munich, for example, and we saw that in the prior interpretation. So this is really helpful for us to see that. One caution about this in SPSS, SPSS will zoom in and look at really finite differences between the means. Whether or not this is a significant amount is something that you need to decide. Literally in this case, we're looking at the difference between $12.10 an hour about for these 2 groups, going up to $12.60. So is 50 cents an hour a significant difference in a real life way? That's not for me to decide, but it would be you, for the researcher, to decide, or for a reader to decide whether that's a significant difference, per hour. I think that's pretty significant, actually, but somebody might look at these differences on the graph and they could look quite large, and the truth is that they're actually not very big. So again, I have the same interpretation here. If you had that chart and in a report, this would be an appropriate way of talking about it. Now, the interaction was not significant, but in this case, but I really want to show you what the chart would look like, and you can sort of appreciate how it was very close to being significant, and I think it's important to see how the differences might appear. So in this case, we've kept city on the x-axis, but now we have two lines representing retail or wholesale as the business type. And an interaction is basically saying the level of salary that we observe in each city depends on or is different at different levels of the other factor, which was business. And while this is not significant, you can sort of see how the trend is definitely there, because I can see that there is a difference in salary or wages earned per hour between the retail and the wholesale businesses. An even greater difference was observed in Munich between the retail and wholesale wages. And in Paris, though, they were pretty much dead on. An interaction might have these lines actually crossed. That could be a real strong sign that there's an interaction. So we were close here, but it didn't work out that it's a significant difference, but we may want to investigate that further. It's definitely a trend that's eye-opening. So the interpretation would be there was no significant interaction for wages between cities and business types, such that wages earned in each city did not differ or depend on the business. And in fact, I would improve this by saying the p-value was greater than 0.05, and which is the level of significance we measured it at. Again, in the prior slide, I showed you if we had set the p-value at 0.1, our interpretation here is that there would be a trend. It's just that our p-value was set too high for us to accept that in this case. All right, last little bit on the type 1 comparisons. Somebody might say, well, why didn't we just do a bunch of t-tests on this to begin with? We could have just set up a bunch of t-tests of wages between Paris and Munich and Paris and London and done that. And indeed, we did end up doing a bunch of t-tests. That's what pairwise comparisons effectively are. But what's happening here is that every single time we're doing an additional test at that same data set, we risk increasing our type 1 error. And that could lead us to finding a result that actually isn't there. We would erroneously reject the null hypothesis. There isn't a difference, but we found one. And we found one because we kept trying to test things over and over again. This is called experiment-wise type 1 error rate. And the formula is actually here, but I think you can appreciate it with this example. Every time that we do one of these tests, there's a multiplicative effect. So if I wanted 95% confidence, which is why I was choosing the 0.05 level, if we multiply up the confidence that we wanted to have, and then we subtract that from 1 to get our alpha, this is no longer 0.05. The reason why we chose 95% to begin with is we wanted to have a good sense that we were effectively outside of that range. If we made an observation that was, greater than 95% of all the values expected in the population, it's weird enough for us to pay attention to it. That's why we chose the 0.05 level to begin with. But you can see what happens when we have a bunch of tests at the same p-value. We're really driving up that type 1 error rate to be something greater than 0.05. We're actually now at a 14% type 1 error rate. What are we going to do about this? Because these pairwise comparisons are what we need to do after we see there's an overall effect, which is the virtue of the Anova. How can we control this type 1 error? Well, luckily, people smarter than all of us have figured this out by looking at different comparisons. So the first thing that we need to do is make sure we have an overall Anova that is significant before we go in and we interpret these post hoc. So this is one check, first of all. Don't go hunting into your data to look at every single pairwise comparison unless you've already found some kind of overall hypothesized result that there is a difference. Secondly, once you have a two-way Anova anyway with an interaction, you're technically not supposed to be looking at the differences between the main effects. This is another check to help you not keep finding a result that's there just from the tests. A lot of times there's the interpretation of the interaction is more important than the main effects anyway. Personally, if you hypothesize that there was a main effect, for example, there is a difference in wages across these three cities, it would be personally fine with me for you to write that up. But there are people who would technically say, as soon as you see a significant interaction, you should no longer be interpreting that main effect at all. And there's a number of reasons for that, but one of them is related to the type 1 error risk, that we're just going to now interpret the interaction and not the main effects. Now, lastly, there's a bunch of statistical adjustments that we can do using SPSS, and we'll be demonstrating these. Fisher's, Bonferroni, Tukey's, HSD. All of these are different methods that we can conduct the tests and then hopefully control for our type 1 error. Fisher's LSD is actually a relatively liberal test to help us find those differences. I think that the Bonferroni and the Tukey are a bit better, and whether or not you use these depends somewhat on how conservative you want to be, and also if the sample sizes vary. Now, you can use Tukey on samples that have different sample sizes. In our example, we had the same number of observations in every level, so this did not apply. But keep in mind that if you have different levels, Tukey would be calculated using the denominator of the smallest group. And so some people say don't use it. And there are these other tests that you can use, Hochberg's and Gabriel's, that are available if you do have varying group size. And both of these can be very good tests. So all of these things help us sort of control that type 1 error being erroneously large. Just keep in mind that we're also making it hard for us to sometimes find an effect if there is one. That's the type 2 or the beta error, which is the other side. So it's a double-edged sword as we're looking at all these different comparisons. So here's the takeaway. We looked today at utilizing variance and our ability to account for it to explain differences within and between groups. And this is a really powerful technique for us to see differences now, especially when we have to compare more than two levels of something or more than two factors. We looked at independent variables and those levels so that we could further understand variance and help us detect differences in populations. This is powerful information. We no longer have to predict the mean for an entire sample. We can start to look at categories of things to help us account for the differences within those groups, which will then help us detect differences between the groups. That's what Anova is doing. We also examined some ways that can help us avoid increasing type 1 and type 2 errors in our analyses by using some adjustments and statistical tests.